Welcome back to our afternoon session. The next speaker, Max Welling from the University of Amsterdam. And his talk is Waves in Artificial Brains, the next wave in neuromorphic computing.
Right. Well, in good tradition, I've changed the title to Space-Time Representations and the Next Wave in Neuro-Inspired Computing. So the core question I want to ask today, and actually not many people will disagree with me at this conference, is are we thinking about machine learning too digital, and should we think perhaps more analog about it? And of course, I've worked at Qualcomm for a while, and we've been quantizing these neural networks, and you can quantize them sometimes to 4 or 2 bits or something like that. It's quite impressive. And so the conclusion is that really machine learning doesn't need all that precision. Now, in fact, we're trying to remove precision by making them by adding noise or dropping out things in order to make them generalize better. So it feels like a huge waste to add all that, to do computations in high precision and then destroy that again by adding noise. Now, brains obviously are also very noisy computing devices. So that's the second piece of evidence. Now, if you look at modern Gen AI methods like diffusion models, for instance, they can be described very precisely with non-equilibrium thermodynamics. So that's a physics model coupled to a heat bath, which again is subject to lots of collisions and lots of stochasticity. So again, there's not a lot of high precision required. And then very recently I heard this story that even in quantum computing this is now starting to pop up. Of course, in quantum computing people fight decoherence. But they found that if you try to, for instance, compute the ground state of a molecule using a quantum computer, it is actually better. So you tend to get into these barren plateaus, which means that you can actually not optimize and everything, all the gradients completely disappear. But if you couple the quantum computer to a heat bath and then cool it down, all of that goes away. And then actually you can minimize them much better. So here's another piece of evidence that even in quantum computing we might be thinking too digital if we think about sort of neural network or variational structures. So the point of this talk is really we should treat machine learning as a physical simulation rather than a very precise digital computation. Now, this has already been observed in 2015 in some sense when this paper came out, which is the root for modern generative AI methods of the diffusion models, which paper was called Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics by these folks. And so here, basically, people think of a learning machine as trying to invert the second law of thermodynamics. So you have some process where you start from structure, which is data, and you start to slowly destroy it using the second law of thermodynamics. In this case, it's Ornstein-Uhlenbeck process or whatever noisy process you prefer. And then you monitor it very precisely at every step, and then you invert that. So it's quite literally unscrambling an egg. And so that again tells you should think about this computation really as embedded in a physical system, a real physical system. And of course, this is the 2021 paper which mapped that to stochastic differential equations, and then you see the pretty dog being noised up, and then the inverse of that process is actually the thing you're after. Now I want to point out that the relationship between physics and machine learning is actually very, very deep in my view. And E.T. Jaynes already knew that a long time ago. This is the guy that invented maximum entropy methods. And he basically stated that statistical mechanics and the introduction of probabilities in statistical mechanics and the introduction of entropy in statistical mechanics is really exactly the same as what we do in Bayesian statistical inference. It is a subjective, it's just expressing our subjective uncertainty about the system. Of course, a real physical system is really in one state and one state only. It's just that we can't track all these degrees of freedom. And sorry for the equations here for those who like it. So so there's this side. We can write down a free energy, and we can bound it by a variational free energy, which is the expected energy minus T times the entropy. This is the famous equation of the variational free energy that people use in statistical mechanics. And this is the same equation, it looks a little different, that we use in machine learning. It's called the elbow, evidence lower bound. And we write minus log px, which is the free energy, is equal to some kind of expected energy, which is the expectation over some variational distribution of the log joint distribution over x, which are our observations, and z, which are our microscopic degrees of freedom that we're not tracking. And then there is an entropy term. And you can make the same derivation and it really maps 1 on 1. So that's one part of the physics. So now let me go to another part of physics, which I will also need, which is symmetries. Symmetries, basically. So symmetries basically can describe or explain much of physics. For instance, this is just a few examples. Electromagnetism was unified under special relativity, which showed basically that if you have an observer that moves with a certain speed, one observer sees an electric field and the other observer sees a magnetic field, so it's really one and the same thing, and so you can connect them using a symmetry. Same thing for general relativity, but the entire standard model is really based on symmetries and can be explained by symmetry. So much of physics can really be understood by thinking about symmetries. And that's one thing that we did in 2016 together with Taco Cohen and later Maurice Weiler and a number of other people, but I'm also mentioning Maurice because he wrote this Bible, and it's all online open access. So if you really like to learn about this topic, feel free to find this particular document. It's very beautifully illustrated. This is one of the illustrations, but there are tons of these. And so the core idea that we will need in the following about equivariance is that there's sort of two types of functions that we want to think about. One function is the function in a neural net that takes you from an input to a filtered version of that input, could be sort of a layer in a neural net. And then there are symmetry transformations which change, let's say, the position or the orientation or something about the input. And then we want that this diagram commutes. So if we first filter and then move in the space, symmetry transform in this space, it should be the same as symmetry transforming the input space and then filtering that thing. And no, the symmetry transformation here can actually be a different operator than the symmetry transformation there, because this could be a different space in which it lives. And so we're going to think about this idea and try to generalize it. And this is work I did with Andy Keller for his PhD thesis. He's now at Harvard, work on the same thing. And so the idea is now that we're going to think of symmetries that are input transformations. So we have input data, and we transform them. So these are transformations of the world. We're going to say that symmetries are input transformations that generate equivalent transformations of the activation layers. So you could think of that, the technical term, as a homomorphic representation. So you take your input, you encode it in some latent space, and then there is a transformation of the input, which means, I could rotate my head, right, and then the sensory input will rotate. But now I want in my brain, basically, something that transforms also my latent representations if I rotate my head. And so the question is, what is that transformation going to look like? But if this diagram closes, we have a proper representation of the symmetry transformations of the input in our latent space. And you could ask, why do I think of this as a transformation or a symmetry? Because for symmetries, we want things to be invariant. We want something to be conserved, like a label or something like this, or an energy or something like this. Well, the way I think of this as at least an approximate symmetry is that the world, at least at the abstract level, doesn't change dramatically. So you're all sitting here. I can close my eyes. I can turn my eyes. The light can go off. All sorts of things can happen to my senses. But I'm pretty sure you'll all be here a few seconds from now, right? And so the world doesn't change very much. It's invariant to these dramatic changes of my sensors. And that's why I think you can interpret this really also as at least an approximate symmetry. And so now I'm going to tie this to something that looks completely different, but it is, I argue, related to this idea of symmetries. And that is that in the brain, more recently, due to the fact that our measuring devices have changed, we now have multi-electrodes, which really can measure many neurons in the brain. And under this new paradigm of measuring many electrons at the same time, many neurons at the same time, people have found that really the brain has a lot of waves that are propagating over the surface of the cortex. And people are trying to figure out what that means, right? What is this a by-effect of brain dynamics, or is this actually something that the brain uses to compute? And so we had the good fortune to actually work with people like Lyle Muller and Terry Sinowski, who are computational neuroscientists, to try to explore this idea. This is from their paper. Here I have another really beautiful example. This is not a model, this is measured, spatially filtered MRI slow fluctuation. So what is this? So this is basically the phase of, I guess, the flow of sort of these MRI activations. And here you sort of see the little vector fields. These little vector fields tell you basically how the flow of those, whatever that fMRI precisely measures, how it flows. But then what you also see is these little blue and red dots. Now those are in physics called topological defects. This is places where the phase will become singular. So some of these places you can sort of see them here a little bit. It's a little hard to see there. For instance, is where if you turn around it, the phase turns by 2 pi, not by 0 if you wrap around it, but actually it changes 2 pi. And so because of its topological defect, these things can only come in pairs. You can create them, but you have to create a blue one and a red one. Or they can annihilate each other, but then a blue one needs to destroy a red one. And the reason is that they are vortices. So in one, the flow goes in one direction, or this direction actually, and the blue one flows in the other direction. So you can sort of imagine that if they come together, they can sort of annihilate each other. Very much like field theory, actually. It's very fascinating. So these are these little particles that are moving around here, and these are actually real measurements in the brain. And so you can think, there's something waving or something moving there. And so going back to this idea of generalized sort of symmetries, here's this picture again. So there's the world, there's some encoding into a brain of the world, there's a symmetry or transformation in the world, right? And then somehow that needs to be reflected in my brain. Some transformation in my brain needs to track that transformation in the world. And so the big question becomes, what are we going to put there? Now, when we did neural networks, it was all very clean mathematically. We could use Lie groups, and we could use representation theory. It was all very clean and nice. But what if you do not know the group representation theory? What if the transformation is not even a group? What if you don't know the transformation at all? Maybe you have to learn it from the data. And so we want to do something more general. So the question becomes, how are we going to move? What are we going to do with those latent transformations in the brain? Okay, so now the idea, I'm going to tie this back to this idea that we need to think less digital. We're going to pretend this is a physical system. Think of it as a liquid of some kind or a gas that's sort of moving around. And so we're going to describe it by a PDE, and the rest of the talk is basically trying out a number of these PDEs and seeing what happens. So here's the first one. So again, same thing. Now he's MNIST, so a bunch of digits which rotate in the real world. And here's the equation that we use for this. I'll maybe quickly go first to the next slide. So this is a paper by these guys here from EPFL, I think, no, for ETH probably. So this is the second order equation that they used. You can think of it as a graph. There's a state in the graph, and then every node is basically has an oscillatory behavior that's coupled to its neighbors. And because it's coupled to its neighbors, you can sort of these traveling waves, right? Now, so basically second order, so you get oscillations. There is these, basically, it depends on the velocity, on the state, depends on the input, so you can drive it. And then there is these damping terms, which make sure that things actually die out as well. So the only thing we did to this was we replaced these sort of matrix multiplications by convolution. So we made it local. We just had every neuron look at the local neighborhood, and then these are the types of latent sort of dynamics you get under this model, and this is the type of latent dynamics you get very naturally when you make that small change, right? And so here's the equation again. So, and you stick it basically into this dynamics for the latent variables. So you have it, this is your data set, and you're training it by saying, okay, encode, propagate here, and then when you decode, you'll have to actually reproduce the future data without looking at it, right? So you will have to backpropagate through this here in order to make these predictions about the future work well. And so the important thing is that we create waves this way, very naturally. So now a little detour, so to think about this slightly differently. So this is the variational autoencoder, which we developed with Dirk Kingma. And so the idea of a variational autoencoder is, again, you have an encoder model, which takes a particular distribution and maps it into a latent space. And there's a decoder model, which you can think of as simulation as well. So it takes a latent space and then it produces basically observations, if you wish, or data points. And you train them together so that both the encoder and the decoder sort of start to work together. So the change we make here basically is to say that so there's an encoder and a decoder still, but now we also have time dynamics in the input space and in the latent space, and that sort of that part is this is a symmetry, or we can interpret it as a symmetry, and this is sort of the symmetry in latent space. Okay, so tying it back to symmetries again. So so this is the rule you need for something to be equivariant, which is if you take your input and you encode it, which is f of x, and then you evolve it, so which is t prime of f of x. This is what's moving here. That should be the same as evolving the input, which is tg of x, and then encoding that input here. And so that diagram needs to close, and then I have approximate symmetries. And so one thing that we wanted to do is to connect this back to see if there's things in here that look a bit like neuroscience. What happens, for instance, can we detect whether the orientation selectivity that will result perhaps after training, will that look a bit like what we found in the brain? So these are sort of these topographic maps. You can think of this as a little piece of cortex. This is an actual piece of cortex. This is a model which we learned. Each one of these colors represents an orientation, right? And you can sort of see that this has a nice and smooth, somewhat smooth, let's say, organization with these interesting pinwheel structures sitting here, where where basically the phase becomes singular. So what do? So we trained a model, and in the latent space, we created these waves, right? So basically in the same way I just mentioned. And then when all that was done, we checked out the orientation selectivity in the cortex, or the sort of the artificial cortex. And then we found exactly this nice topographic structure in there. I don't know precisely why that is, I should say. So if there's some neuroscience that understand this better than I do, but it is kind of nice that happens. Okay, so here's another model that we tried to just see, okay, how easy is it actually to get these waves into models, right? And so again, so this is a very simple RNN, an iRNN, where you take the next state over time as a nonlinearity, a linear map times the previous hidden state, driven by the input as well, and a bias, and you train this on some task. For instance, a task where you need to read something in memory, hold it in memory, and then reproduce it like an amount of time later. Or you do an actual little computation, like add two numbers. You have one number, you add another number, you add them, you hold them in memory, and then you reproduce them sometime later. So again, very simple change. We change this with a convolution, and there's some little trick with initialization, but it's not all that not significant. Now, what did we get out for this model once we trained it on these types of tasks? So this is the sort of the hidden unit structure for this model, and here what you see is basically the hidden structure for the for the model, the RNN model. Now what happens is basically it will read in a particular piece of information, and then it has a stack of channels, and then it will basically move the information at every time step. It will move it one up the ladder. It just runs it up the ladder, and then and the other side it will wrap back. So it'll just start moving around on a circle, all these pieces of information, and then it can hold it in memory for a very, very long time. And once it's time to reproduce it, it just then decodes these sort of waves, this sort of information that was held in these registers. It decodes it and then sort of gives the answer. And it really has a amazing improvement if you look at training normal RNNs in terms of keeping things long in memory. So this is like an adding task, and you need to have it 1,000 steps in memory. A normal RNN completely fails at it, but these wave-like structures actually do quite well. All right. And so this is then a slightly different topic, but again on the same idea, which is that we were also thinking, can we use the same idea to think in a different way about disentangling? So disentangled representations are a very confusing field. There's like 10 definitions of what it means for a representation to be disentangled. So we thought, well, let's add an 11th one. And so the idea is here to think about a disentangled representation in terms of the dynamical, the changes to it representation rather than a static definition. We just want a representation to have sort of, if I give you a particular image, that you understand there are sort of independent ways in which you can change that representation into something else. For instance, you can move it, you can rotate it, you can change the lighting, you can change the coloring. These are independent ways in which you can manipulate a particular representation. And can we find good representations that give you all these directions, these independent directions in which you can change a particular input? So you have an input, so you encode it, and then there's not only the actual code for that input, but there's also these velocity vectors which tell you how to change that under a particular transformation. You call it a symmetry. So in this particular direction, let's say, it would first change color, and then you would maybe go use a different direction, and it would change orientation. Sorry, yeah, I guess orientation and color and scale or something, and here would change scale, right? So you could just choose linear combinations of these velocity vectors, and you would have control of how to change that. And we modeled that again. In this case, this model that would run here would be sort of a liquid, or basically a continuity equation. So it feels a bit like a liquid in some sense. And so here we improved it. So we completely trained this completely unsupervised. So you don't have to tell it what the actual transformations are. You just give data and just like independent component analysis, just figure out what the independent transformations are. The velocity fields can now have different speeds, so some transformations can go faster than other transformations, etc. And then you get sort of results that look a bit like this. So these are the independent components that it figured out. By the way, we didn't only look at MNIST, we also have others, but I won't show it here. So these are the independent components. So it found out that there are threes, and you can rotate threes. You can rotate them faster as well. So there's so here's a unit that scales things. So these are the velocity fields that change things. Here are things that rotate it and scale, and then here are things that change color, for instance, right? And you can do this at every point. You can take an arbitrary point, you can encode it, and then you have one velocity which rotates it, another velocity which scales it, etc. So I would say that is a good definition of a disentangled organization, not just a code for what it is, but also a code for how to change it. And you can do fun things now. You can, of course, just do new trajectories it's never seen before. So you can first take a 3 and then change color, and then take another vector field and then scale it. Or you can do many things. So you can also take linear combinations of transformations. So here we can both rotate it and scale it, or rotate it and change color. And of course, it's never seen these things actually, right? It's just known how to combine these things naturally. So here's a bit of a little bit of the same idea, but now applied to a real, maybe interesting problem in neuroscience. So this is a benchmark where people have measured, let's say, monkeys doing a particular task in front of a screen. So this particular task, there's many more, but this is one where the monkey needs to sort of move its hand from one position to another, but it's constrained, so it has to move in sort of it cannot move in a straight line. It'll have to move around blocks. And then there's this Poisson data, these spike data, and then you'll have to try to predict, what the trajectories of the hand are. And so here, we have the same model. Actually, there's also lines here. So we have transformations on the input, which is basically this. There's transformations in the hidden space, which we now model with Langevin equation, which is, the change in position is given by velocity. The change in velocity is given by, again, a friction term, a potential, a force, basically, and a random kick, which is the Brownian part. And then there's a decoder, which is a Poisson model. And so when you, oh, that's kind of weird. Yep. And then when you look at sort of the data, I mean, of course, there's numbers and all that, but so at least you can see here that it's a pretty reasonable reconstruction of, so these are the data and these are the reconstruction of our model and test data. So you can see that it can pretty good reconstruct the trajectories of the monkey's hand. All right, so then I'll close. So my point for this presentation was that I want to argue for the significance of space-time or spatial temporal representations in machine learning. We should think about traveling waves and as a new way perhaps to encode information also in neural networks. I've argued that it's related to non-equilibrium thermodynamics and diffusion models, especially in traveling waves. I would think that traveling waves encode long-range information. So if you want to move some piece of information from one side of your representation to the other side of a representation, a wave is a very stable way to do that. It's related to symmetries and equivariance. It can be used to define a new type of disentangled representations, and it can serve as memory, basically, because it's a stable structure. And so, not surprisingly, the next, and I think many people agree, but the next generation of machine learning hardware should probably be less digital and more analog or on physics neuro-inspired in some sense, because it is the natural way to model in machine learning. Thank you. I'll stop there.
Thank you. Thank you for your great talk. Are there any questions in the audience? Then just... Just state your name and your affiliation shortly.
Hello, I'm Cedric Goumare from Ghent University, and I was very inspired by your talk about your model with convolutional RNN, and especially the visualizations. It makes a lot of sense to look at it from a local neuron interaction perspective. But I was wondering, in terms of the link with the brain, convolutions are also weight sharing in a sense.
Yep.
So could you also achieve this model with local interactions but not weight sharing, which would be more biologically plausible?
Right. Well, I would argue that weight sharing is a very good prior in some sense because it encodes translation equivariance. So I think the brain probably has something like that in some sense, certainly on your retina, I guess. So it is a natural prior, but certainly if you approximate that by maybe things which are a little bit different, you will still get waves, but maybe the waves would, slightly change in their properties as they propagate, right? It might not be a very clean sine wave or something like this. It might be that it starts to bend or it starts to accelerate or the frequency changes a little bit or something like that. But yeah.
Okay, thank you.
Yeah, this is pretty cool. Thanks for the presentation. I fully stand behind the mission of physics and neuro-inspired AI. But
who are you?
Say again.
Who are you? Because you.
Yes. Andre Alexandru, affiliations, Alice Network, Radboud University, Artificial Cognitive Systems Lab.
Thank you.
All right. Did you put any thought into AI-inspired physics, meaning into autonomous agents that can help us gain a better understanding of our universe? And do you see any meaningful directions in that effort?
So I would say I didn't go that far. So having autonomous agents doing science for us and just, basically taking our jobs. But I do think machine learning has a huge role to play in accelerating science. In fact, I just started a startup that is using AI to design new materials. And so that way, machine learning can really help. Using these diffusion models, by the way, you can generate molecules, and then you can test them using chemistry. And then that way, you can sort of very quickly search through the haystack of molecules with certain described properties. And I think that would definitely, I strongly believe in that because I started a startup on it, and I think it's going to revolutionize material science.
Nice, thanks.
Thank you for this very nice talk, which also made me very happy as an algebraic topologist to see some commuting diagrams here in machine learning and neuroscience. One question regarding timescales. Have you looked at how certain heterogeneity, for example, of timescales influences dynamics? I assume all those timescales were the same here. And then also how, because you've shown oscillating networks, intrinsically oscillating, and non-oscillating ones, first order ones. Have you looked at certain differences there also in terms of representation?
Yeah, great question. So actually, everybody was asked to state who they are, so I'm just reminding you that.
Felix Effenberger from ESI Frankfurt.
All right. So this particular model here was precisely meant to change, to have different time scales. So what happens here is that you have different transformations, but the transformations are multiplied by a number, and the number can speed things up and slows things down. So in this model, there is different time scales involved. And then the other question was about overdamping and underdamping. So I think that's a great question. So if you have an underdamped system, and then there's also noise and no noise. So there's basically, if you have an underdamped system, you have no noise. Basically becomes a normalizing flow, basic continuity equation. That's basically you take a particular, let's say, probability distribution, and you just push it, you just translate it, you just transform it. And then there's another one where you add noise, and so you get diffusion as well. And then the more interesting ones is where things start to oscillate, as you agree, right? Where, now it's second order, and so now things start to sort of oscillate around, and you get traveling waves, and you can add noise to that as well. And yeah, I think I personally would. So sometimes it's a little easier to train the ones without the oscillations, but I think there's very interesting things happening with the oscillations. So I'm definitely betting my future on the oscillations part. That's, I think, where the more interesting. That's also where the traveling waves. I mean, in the brain they actually do see the oscillations. They do see the traveling waves, and so it'd be very nice to explain that better. Yeah.
Thank you.
Hello. Thanks for the nice talk. I'm Rishabh Malik from Forschungszentrum Jülich. So I myself, I did my master's in physics, so I had done quite a bit of particle physics and equivariance and symmetries that kind of give rise to the couplings between these particles.
Nice.
So I was really intrigued by the fact that when you talked a lot about projecting these real space, data into latent space and transforming them there and projecting them back. So when you do this mapping between the latent space and the actual data, these mappings, do they have to be designed in some way, they have to be equivariant, or they can be any neural network that you can train it and
Yeah, great question. So we didn't design them, we just learned them as an encoder and a decoder like you would do in a VAE. Of course, when you build equivariant networks, you actually do design them. But in this case, that's when you change something, you want all your latent representations to change with it. So you could argue that if you have something that's that has an equivariant structure, and you encode it, that could be very helpful. That if you rotate something and it's the same, you encode it again sometime later, at least it's rotated by the right amount. But the point here was that what we really wanted is to move away from this this constraint that you need to understand the representation theory of the group. And so we just let it, we just said the only prior we're going to put on this is that you should behave like some kind of liquid. Because basically you should be some kind of, described by some kind of continuity equation or a Langevin equation or something like that, some kind of PDE that looks like that. And then let the whole system figure out basically what the dynamics, when it learns it, what the dynamics should be. So we didn't actually put in the wave-like patterns, but we gave it quite a bit of hints that we like waves. So we had local connectivity and these kinds of things. But it's not given that it will figure it out, but it learned to then produce these waves. Yeah.
So it's kind of a more general network which kind of learns the transformations on its own. Like you're not like hard coding that into the network. It's even if it's shift invariance in cases of like images, it kind of learns it on its own. Like there's shift invariance in images and stuff.
Yeah. So we do. I would argue that the fact that we tell it needs to live in a certain dimensional space, and we want to describe it by a PDE is actually quite a bit of prior knowledge, and so that is a big prior. But we didn't actually build in the equivariance, the actual symmetry itself. That it had to sort of figure out. Yeah.
Thank you.
Okay, thanks again to Max Welling.